Hi folks. So in last lecture, we have seen two methods. One is indexing, another one is hashing. And we have seen the pros and cons of both of this method, correct? Now the third method is using BTree. Okay. So in the last lecture, I have already told you like how an hard disk works, but let's dig a little bit deeper. Okay. So like we know in a hard disk, this one block is called a block. Okay. And I made a small mistake in the last lecture. I have told that each block is 500 KB. I was wrong. Each block is 500 bytes. Okay. Okay. Now let's see. You are storing. Uh, let's think of a database. Okay. Let's think of a database. So it contains like ID, name. Okay, and it contains department. It contains subject. Okay, and it contains the address. Okay, this is a table. So let's say this is like for example 10 bits, this is 50 bits, this is 10 bits, subject is let's say 8 bits, and address is let's say 50. Okay, so the total, so each row is basically 128, each row is 128 bits. Okay, so for reading each block, we have to read 128 bits. Now, as I have told in the last lecture, that each block is of 500 KB, sorry, 500 bits. Okay, so each block can contain 4 rows at a time. Okay, okay, cool. Now let me draw the table again. Okay, okay, whatever, like 1, 2, 3, 4, 5, whatever. Akash, Ashish, Bob, Krati, Kantamai, okay, whatever. Now, if you want to read, if you want to search Krati, what you have to do, you have to read all these 4 rows, and then from there you have to read Krati. But let's say there are millions of like data. Okay, let's say there are millions of data. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's say Krati exists somewhere here. Okay, so what you have to do, in first go you can only read this 4, block number 1. Okay, then in block number 2 you can read next 4. Okay, in block number 3 you can read Krati. So if let's say for reading one block you need 1 second, so for getting till Krati you have to like waste 3 seconds. Okay, but let's say Krati is not even here, it is like after reading 30-40 blocks you can read Krati. That is disastrous. Like for reading one name you have to like waste 30 seconds. So what we can do, so let's say again this is our DB. Okay, so this 4 is in one block, 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 and there is a metadata. Okay, and let's say these are shorted. Okay, so from A to C, oh, it is here. From D to let's say Q, it is here. From Q to Z, it is here, and Z to Y, it is here. Okay, we have a metadata. Okay, and let's say there is like each row contains of like let's say 50 bytes. Okay, so we can literally take like we can literally have 10 rows inside this, and the metadata of this block is stored here, this is stored here, this is stored here, this is stored here. Okay, and blah blah blah, whatever. So now let's say Krati is over here. Okay, so previously for searching Krati you have to read like 1 block, 2 block, 3 block, 4 block, so wasted 4 seconds. But now the user will go here in this metadata, I want to search any name Krati, where can I find it? So it said that K should be present in this block. You directly go to this particular block. Okay, so here you have to read one block for getting the whole metadata and one block to get this whole information, and from here you get Krati directly. So you have to waste 2 seconds. So previously it was 4 seconds, now it is 2 seconds. Okay, let's say even this, let's take third example. Okay, so there are like millions of entries. There is one metadata table, there is two metadata table, okay, which contains like some informations. Again, here it contains some informations, okay, and there is a final metadata which contains like information of this, or many like this. Okay, so if I just just rotate this, you can see it is a B tree. Okay, where this is the root, these are the child nodes. Correct. So this is why in B tree, amount of time required to amount of time required for uh, reading a data is much lesser than that of hash table, and that of obviously in hash table it is O of 1, but much less than index. Okay, but the second thing is, the second benefit is, in hash table you cannot do range queries. So let's say you want to read all the data, start all the names starting from A to, let's say, C. In hash table you cannot do it. Why? Because like in hash table, like random numbers are generated, so you cannot just, you have to like read all the data to get like all the names between A to C, which is literally O of 1, O of n, correct? But in binary tree, like I have told you, we have this, then let's say this, okay, and then we have like this, this, okay. So we and let's say this is from A to like Q, and this is from like rest of the data Z. Okay, here also we have like A to B, B to C, sorry, C to D, and rest D to like Q. Here we have like let's say E, like D to F, then F to Q. Okay, so you can see if you need all the names from F to Q, you just have to traverse, like just have to do depth first search and you can reach here. So the time complexity is extremely low. So what we have seen, like in B tree, the best things are data is persistent. Okay, persistent. The B tree is saved inside a hard disk. Okay, so the data is persistent. Two, time complexity is very less. Time complexity is very less. Third is you can do range queries, which we cannot do in hash functions and indexing, because in indexing, whatever the spelling is, yeah, so we cannot do in hash functions and indexing. So yeah, this is what BTree is. There is little bit modifications in different kind of database, for example B plus tree. Okay, so what happens in B plus tree is basically in this nodes data is not stored. Okay, in this node data is not stored. In this nodes we just go till leaf node, and leaf node has a pointer where data is stored. Okay, leaf node has a pointer where data is stored. Okay, and each leaf node has address to the another leaf node also. So here the range query is even more faster. Okay, here the range query is even more faster. Why? Because let's say from here we have A to D, and over here we have E to, let's say, H. Okay, and you want to search every name from B to, let's say, F. Okay, so you have read here from B to D. Okay, B to D you have read here, and from this linked list, kind of like it's not linked list, but it kind of treats like a linked list. You have E to F. You can read E to F for data also. Okay. So yeah, in B plus T it is even more optimized. So in this lecture, what we have seen, like why not to use hash function and indexing. Okay. What is B-tree? Like why we use B-tree, not exactly what is B-tree. You can find in YouTube many channels who are saying like what is B-tree. And like from B-tree, which is even better solution is B plus tree for range queries. B plus tree is nothing but B-tree where the information is not stored in nodes. The information is stored in leaf nodes. The leaf nodes have the pointer to the place where the information is stored, and the leaf node contains pointer to the next leaf node also, due to which the range queries are even faster. It is very good for write, very good for read. Okay, but there is a better solution which is LSM trees, but we will read about that in the next lecture. Thank you.